In October 2017, something entered our solar system. It came from the stars. It moved in ways we could not explain. Scientists called it Oumuamua, and no one knows what it really was. Welcome to Sleepy Science Nights. Tonight, we explore one of the strangest moments in modern astronomy, the story of an object that should not exist. In the autumn of 2017, a telescope in Hawaii detected something unusual, a dark shape moving through space. At first, scientists thought it was a comet. Then they thought it was an asteroid, but the more they looked, the stranger it became. It was shaped like nothing they had ever seen, long and thin, tumbling through the void, moving faster than it should. And most puzzling of all, it was accelerating. Something was pushing it. But there was no tail, no trail of gas or dust, nothing to explain the force. They named it Oumuamua. In Hawaiian, it means scout or messenger, the first to arrive from a distant place. Because this was not a comet from our solar system. This was not an asteroid from our asteroid belt. This was a visitor, an interstellar traveler, the first object we have ever detected that came from another star. It passed through our neighborhood at more than 54,000 miles per hour, silent, dark, undisturbed by our curiosity. And then it left. We will never see it again. But the questions it raised remain. What was Oumuamua? Where did it come from? How long had it been traveling through the galaxy? And why did it behave the way it did? Tonight, we will follow the data. We will explore the theories. We will walk through the quiet mystery of the universe's first confirmed messenger. This is a story about discovery and wonder, about the limits of our knowledge and the vastness of the cosmos. So settle in. Let your mind drift. And join us as we explore the alien object that visited Earth. If you enjoy drifting off to the mysteries of space, consider subscribing. We create long-form science documentaries designed to soothe, educate, and guide you gently toward sleep. Let's begin. October 19th, 2017. A telescope on the island of Maui was scanning the sky. The telescope was part of a project called Pan-STARRS, Panoramic Survey Telescope and Rapid Response System. Its job was to watch for asteroids, objects that might one day threaten Earth. Every night, it swept across the heavens, photographing the same patches of sky over and over, looking for anything that moved. On this particular night, the telescope captured an image, a faint streak of light, moving against the background of stars. At first, no one noticed. The data was processed automatically. Software compared the new image with older ones, looking for changes. And the software flagged something, a moving object, fast, unusual trajectory, not following the path of a typical asteroid. The alert went to astronomers at the University of Hawaii. They reviewed the data, and immediately they knew something was different. The object was moving too fast, and in the wrong direction. Most asteroids orbit the Sun in roughly the same plane. They move in predictable ellipses. But this object was different. Its path was hyperbolic, not an ellipse, a hyperbola. That meant it was not bound to the sun. It was not orbiting. It was passing through. The astronomers ran the calculations again. They checked for errors. But the numbers held. This object had come from outside our solar system. It had entered from interstellar space, traveling between the stars. And now, it was leaving. It had already passed closest approach to the sun. It was already on its way out. They had discovered it on its way out the door. The realization was staggering. For decades, scientists had theorized about interstellar objects, rogue asteroids, comets ejected from distant star systems, wandering the galaxy. But no one had ever seen one. Until now. The astronomers sent out alerts to observatories around the world. We have something. You need to look at this. Within hours, telescopes were turning toward the coordinates. In Chile, in Arizona, in California, in Spain. Every major observatory that could see it pointed in its direction. Because this was a moment in history. The first time humanity had detected a visitor from another star, the object was faint, very faint. It reflected almost no light, dark as charcoal, and it was already moving away from us. Every day it grew dimmer. Every hour it slipped further from view. The astronomers knew they had only a short window, a few weeks at most, to gather every piece of data they could, to photograph it, to measure its light, to understand what it was, because soon it would be gone forever. They named it 1I. The designation for the first interstellar object ever detected. 1I 2017 U1. But that felt cold, clinical. This was a historic discovery. It deserved a name. The Pan-STARRS team suggested Oumuamua, a Hawaiian word. Oumuamua. It means scout or messenger. The first to arrive from a distant place, sent ahead to observe. The name was perfect, because that is what it was. A scout from the stars, a messenger from the deep, the first of its kind to visit our solar system. And we almost missed it. If Pan-STARRS had not been watching that particular patch of sky, if the software had not flagged the movement, if the orbit had been slightly different, we would never have known. Oumuamua would have passed through in silence, unseen, unnoticed. Just another shadow in the dark. But we did see it. And what we saw changed everything. Because Oumuamua was not like any asteroid we had ever studied. Its shape was wrong. Its color was wrong. Its behavior was wrong. And the more we learned, the stranger it became. The night it appeared, we thought we understood the universe a little better. We thought we knew what asteroids looked like, what comets looked like, what to expect from the debris of distant stars. But Oumuamua did not fit. It defied our models. It challenged our assumptions. And it left us with more questions than answers. This is where the mystery begins. On a quiet night in October, in a telescope on a volcanic island, watching the stars, waiting for something unexpected, and finding it. The first visitor, the alien object, Oumuamua. After the discovery, the observations began in earnest. Telescopes across the world locked on to Oumuamua. They tracked its position. They measured its brightness, and immediately something seemed off. The brightness was changing, not gradually, but dramatically. Over the course of just a few hours, Oumuamua would brighten, then dim, then brighten again. The changes were extreme, a factor of 10, sometimes more. This told astronomers something important. Oumuamua was tumbling, rotating end over end. As it spun, different surfaces reflected sunlight toward Earth. When a broad side faced us, it brightened. When a narrow edge pointed our way, it dimmed. By measuring the timing of these brightness changes, scientists could calculate the rotation period. Oumuamua tumbled once every 7 to 8 hours. That was unusual, but not impossible. Asteroids tumble, especially small ones, especially ones that have been knocked around by collisions. But the magnitude of the brightness variation was shocking. A factor of 10 suggested something extreme, an object that was not round, not spherical, not even lumpy and irregular like most asteroids, something elongated, very elongated. The scientists ran simulations, they built models. They tried to match the observed brightness curve with different shapes, and the only shape that fit was astonishing. Oumuamua had to be at least 5 to 10 times longer than it was wide. Some estimates suggested even more extreme proportions, 10 to 1, perhaps even more. Imagine a cigar, or a needle, or a shard of metal, long and thin, spinning slowly through space. No asteroid in our solar system looks like that. Asteroids are battered, broken, smashed by billions of years of collisions. They are lumpy, potato-shaped, irregular, but not stretched, not elongated like a pencil. Gravity does not allow it. If an asteroid is too elongated, it breaks apart. The forces are too great. The structure cannot hold. And yet, here was Oumuamua, spinning, stable, intact, with a shape that defied our expectations. Scientists estimated its size. Based on the brightness and the distance, they calculated dimensions. Oumuamua was roughly 1,300 feet long, about the length of 4 football fields, but only about 130 feet wide, maybe less. A slender thread of rock or metal, dark, reddish in color, reflecting only a small fraction of the sunlight that hit it. Its surface was old, weathered, bombarded by cosmic rays for millions of years, perhaps billions. The reddish tint suggested organic compounds, tholins, complex molecules formed when simple chemicals are exposed to radiation over vast timescales, similar to the surfaces of some objects in the outer solar system. Pluto has tholins. So does Triton. So do some comets. But Oumuamua was not from our solar system. This reddish crust had formed somewhere else, under a different star, in a different cloud of debris. And it had been traveling through the void for an unimaginable span of time. The shape remained the most perplexing feature. Astronomers debated. Was it a single solid object? or two objects stuck together, a contact binary, two lobes touching? That might explain the elongation. Two asteroids gently collided, now traveling as one. But even that seemed unlikely. The brightness variations were too smooth, too consistent. A contact binary would show irregularities, wobbles, asymmetries. Oumuamua's light curve was almost elegant, mathematical, as if the object were a single piece, uniform, streamlined. Some scientists suggested it might be a fragment, a shard broken off from a larger body, ejected during a violent collision in another star system, sent tumbling into the galaxy. That could explain the shape, a splinter of a shattered world. But even that raised questions. How could such a fragile shape survive the journey? Interstellar space is not empty. There is gas, dust, tiny particles. Over millions of years, impacts would erode the surface, chip away at the edges, round off the extremes. And yet, Oumuamua remained needle-like, sharp, defined, as if it had not been traveling for very long, or as if it were made of something incredibly strong. Something that resisted erosion. The mystery deepened. Every measurement raised new questions. Every model required new assumptions. And all the while, Oumuamua was speeding away, growing fainter, slipping beyond the reach of even our most powerful telescopes. The shape of Oumuamua became iconic. Artists drew it as a sleek shard, a crimson needle, a cosmic splinter. News outlets showed renderings, long, thin, mysterious, tumbling against a backdrop of stars. But those images were guesses. We never saw Oumuamua's true shape. It was too small, too far away, too dark. Even the Hubble Space Telescope could not resolve its surface. All we had were the brightness variations, the light curves, the mathematical models, and they all pointed to the same conclusion. Oumuamua was unlike anything we had ever seen, a visitor from the stars, shaped like a message we could not read, long, silent, strange, and already gone. As the observations continued, astronomers plotted Oumuamua's trajectory with increasing precision. They measured its position night after night, calculating its path through the solar system, where it came from, where it was going, and how fast it was moving. The trajectory should have been simple, predictable. An object passing through the sun's gravitational field follows a specific path, a hyperbola, determined entirely by its speed and angle of approach. Newton's laws, Kepler's laws, gravity, nothing else, but something was wrong. Oumuamua was not following the predicted path. It was deviating, slightly, but measurably. It was accelerating, moving faster than it should, as if something were pushing it. At first, scientists thought it was an error, a mistake in the calculations. Perhaps they had miscalculated the mass of a planet, or overlooked some small gravitational perturbation. But they checked and checked again. The numbers held. Oumuamua was definitely accelerating, and not in a random direction. The push was directed away from the sun, outward, as if something were propelling it on its journey. This was deeply puzzling. There are only a few things that can cause a non-gravitational acceleration in space. For comets, the answer is obvious: outgassing. When a comet approaches the sun, it heats up. Ice turns to gas. Jets of vapor erupt from the surface, and those jets act like tiny rocket engines, pushing the comet, accelerating it, changing its trajectory. Astronomers see this all the time. It is expected. Normal. But Oumuamua showed no signs of outgassing. No tail, no coma, no cloud of gas or dust. Telescopes searched for any hint of activity. Spectroscopy, infrared imaging, radio observations. Nothing. Oumuamua was inert, dark, silent, and yet it was accelerating. The scientists ran models. Could there be outgassing that we simply could not detect? Very faint. Minimal. Just enough to produce the observed acceleration, but not enough to create a visible tail. It was possible. If Oumuamua were made mostly of ice, and if that ice were sublimating very gently, releasing gas in such small amounts that it remained invisible, that could explain the push. But there were problems with this idea. First, the amount of outgassing required was precise. Too little, and you would not get the observed acceleration. Too much, and you would see a tail. The balance had to be perfect. Unlikely. Second, if Oumuamua were a comet, it should have been brighter. Ice reflects sunlight well. But Oumuamua was very dark. It reflected only about 4% of the light that hit it, as dark as charcoal, or asphalt, not like ice. Not like a typical comet. Third, the shape, that extreme elongation. Comets are not shaped like needles. They are irregular, lumpy, fragile. A comet shaped like Oumuamua would break apart. The stresses would be too great. And yet, the outgassing hypothesis remained the most plausible explanation. Because what else could it be? Some scientists suggested radiation pressure. Light from the sun carries momentum. Photons push, very gently. But over time, that push can affect small objects. Solar sails use this principle. Spacecraft with large reflective surfaces can be propelled by sunlight alone. Could Oumuamua be responding to radiation pressure? The scientists calculated. For radiation pressure to cause the observed acceleration, Oumuamua would need a very specific geometry. It would need to be extremely thin, less than 1 millimeter thick. A sheet, a flake, not a solid rock. That seemed impossible. No natural process creates objects that thin and that large. It would be like a piece of paper the size of a football field, floating through space, intact, unbroken, for millions of years. The idea was too strange. And yet, the acceleration remained unexplained. As the observations ended and Oumuamua faded from view, the mystery lingered. Something had pushed it. Something had changed its trajectory, ever so slightly, but definitively. The data was clear. The explanation was not. Some embraced the comet hypothesis despite the lack of visible outgassing. Oumuamua must be a comet, they said. Just an unusual one. A comet we do not fully understand. Others remained skeptical, unconvinced. The acceleration was real, but the cause was unknown. And in that unknown space, other ideas began to emerge. Ideas that were more speculative, more controversial. Ideas that suggested Oumuamua might not be natural at all, but we are getting ahead of ourselves. For now, we remain with the data, the observations, the measurements. An object from another star, shaped like a needle, dark as shadow, accelerating away from the sun, for reasons we could not explain. A mystery written in motion, a puzzle encoded in deviation. The mysterious push, the unexplained force, the phenomenon that turned Oumuamua from a curiosity into an enigma, and the questions multiplied. What was it made of? Where did it come from? How long had it been traveling? And most intriguingly, why did it behave the way it did? The acceleration was small, but its implications were vast. Because if we could not explain the motion of this object with our current understanding of physics and astronomy, then perhaps Oumuamua was trying to tell us something we were not yet ready to hear. A message from the deep, written in the language of force and trajectory, waiting for us to decode it. To understand Oumuamua, we must understand where it came from. Not just which star, but which epoch, which era of the galaxy. Because Oumuamua did not begin its journey yesterday, or last year, or even 1,000,000 years ago. By tracing its trajectory backward, astronomers attempted to determine its origin. They calculated the angle of approach, the speed, the direction, and they ran the numbers backward through time, rewinding Oumuamua's path through the galaxy, looking for a home. The task was monumentally difficult. The galaxy is in constant motion. Stars orbit the galactic center. They drift, they wobble. They move in complex patterns influenced by the gravity of neighboring stars, gas clouds, and dark matter. Over millions of years, everything shifts. And Oumuamua had been traveling for a very long time. The calculations suggested it came from the direction of the constellation Lyra, near the bright star Vega. But not from Vega itself. Vega was not in that position millions of years ago. The scientists looked deeper. They searched for any star that might have been near Oumuamua's path in the distant past, a birthplace, a point of origin. But the search turned up nothing definitive, no obvious candidate, no nearby star system that aligned perfectly. Oumuamua's origin remained a mystery. It had come from somewhere, but we could not say where. This was not entirely surprising. Interstellar space is vast. The distances between stars are immense, and objects like Oumuamua travel slowly compared to the age of the galaxy. At 54,000 miles per hour, Oumuamua sounds fast, and by human standards it is. But in galactic terms, it is almost standing still. Traveling at that speed, it would take Oumuamua 70,000 years to cover 1 light year. The nearest star to our sun is over 4 light years away. That is nearly 300,000 years of travel, and most stars are much farther. If Oumuamua came from a star 10 light years away, it had been traveling for 700,000 years. If it came from 100 light years away, 7 million years. If it came from the other side of the galaxy, billions of years. Deep time, geological time, cosmological time. Oumuamua was not a recent traveler. It was ancient, a relic, a piece of the past. Its surface bore the marks of its journey, the reddish color, the dark, weathered appearance. These were the scars of cosmic rays, high-energy particles that sleeted through interstellar space. Protons, electrons, atomic nuclei traveling at nearly the speed of light. Over millions of years, these particles bombard any object in their path. They break chemical bonds. They alter molecules. They darken surfaces. They create complex organic compounds called tholins. Reddish, brownish, chemically rich. The same process happens in the outer solar system. But Oumuamua's exposure was longer, harsher. Interstellar space is colder than the space between planets, only a few degrees above absolute zero, and it is more exposed. No star nearby to provide warmth, no planetary magnetosphere to deflect radiation, just the raw galactic environment. For eons, Oumuamua survived it all. It did not shatter. It did not disintegrate. It held together. This suggested it was made of something strong, rock perhaps, or metal, or a tightly packed mixture of ice and dust. Something cohesive enough to withstand the stresses of deep time and deep space. But how did it become interstellar in the first place? How does an object escape its home star system and wander the galaxy? There are a few possibilities. 1. Planetary formation. When stars are born, they are surrounded by disks of gas and dust. Over time, that material clumps together, forming planets, asteroids, comets. But the process is chaotic. Gravitational interactions between growing planets can fling smaller objects outward, ejecting them, sending them into interstellar space. This happens in our solar system too. Jupiter and Saturn have ejected countless comets over billions of years. Most never return. They drift into the void. Oumuamua could have been ejected during the formation of a distant planetary system. Billions of years ago, cast out by a giant planet, never to return. 2. Stellar encounters. Sometimes stars pass close to each other, not colliding, but close enough that their gravitational fields interact. This can disturb the outer regions of their planetary systems, sending comets and asteroids into new orbits. Some fall inward, some are ejected. Oumuamua might have been shaken loose by a passing star millions of years ago in a neighborhood we cannot identify. 3. Catastrophic events. Collisions. Supernovae, the death of a star. When a massive star explodes, it releases an unimaginable amount of energy. The shockwave tears through its surroundings. Any nearby planetary system would be shredded, planets vaporized, smaller objects flung outward at tremendous speed. Oumuamua could be debris from such an event. A survivor, a fragment of a world that no longer exists, orbiting a star that is now a neutron star or black hole, or perhaps no star at all. We do not know. We may never know. But what we do know is this: Oumuamua is not unique. It cannot be. If one interstellar object passed through our solar system, there must be others, many others. Most go undetected, too small, too dark, too fast, or passing through regions of space we are not watching. Astronomers estimate that there could be thousands of interstellar objects passing through the solar system at any given time. Most the size of a house, or a car, or smaller, invisible to our current telescopes. Oumuamua was simply the first we happened to catch, and we caught it late. Already leaving, already accelerating away. If we had detected it a few months earlier, on its way in, we might have had more time, more observations, more data, perhaps even a mission, a spacecraft sent to intercept it, to photograph it up close, to measure its composition, to answer the questions that now haunt us. But we did not. And now Oumuamua is gone, hurtling out of the solar system at 60,000 miles per hour, heading toward the constellation Pegasus. It will travel for hundreds of thousands of years, alone, silent. Until perhaps, one day, it enters another star system. And maybe, just maybe, another civilization will see it and wonder, where did it come from? What is it made of? Why does it move the way it does? And they will give it a name in their language, and they will debate its meaning. Just as we have. Oumuamua, the traveler from deep time, the wanderer of the galaxy, a messenger we could not quite read, but one we will never forget. The acceleration, the shape, the silence. These three mysteries converged into a single, unavoidable question. What if Oumuamua was not natural? It is a question most scientists hesitate to ask, for good reason. Throughout history, humans have looked at the unexplained and leapt to extraordinary conclusions. Lights in the sky became gods. Patterns in nature became omens. The unknown became the supernatural. Science teaches us to resist that impulse, to seek ordinary explanations first, to exhaust every natural possibility before considering the extraordinary. But what happens when the ordinary explanations do not fit? What happens when every model requires assumptions that stretch credibility? What happens when the data itself seems to point towards something we have never encountered before? This was the position some scientists found themselves in with Oumuamua, not because they wanted to, but because the object defied explanation. Dr. Avi Loeb, a theoretical astrophysicist at Harvard University, was one of the first to ask the question publicly. What if Oumuamua was artificial? Not a rock, not a comet, but a piece of technology. The suggestion was met with immediate controversy. Some called it irresponsible, others called it sensationalism. Many dismissed it outright. But Loeb did not back down. He pointed to the evidence, the extreme elongation. No natural process easily explains a 10:1 length-to-width ratio, especially for an object that size. The mysterious acceleration. Comets outgas. But Oumuamua showed no signs of it. No tail, no coma, no detectable emissions, and yet it accelerated, as if pushed by something invisible. The reflectivity. Oumuamua was dark, reflecting only 4% of the light that hit it, But if it were made of metal, or coated with metal, it could still appear dark, especially if the surface were weathered or oxidized. Loeb proposed a specific hypothesis: a light sail, a thin, reflective sheet, designed to catch the pressure of starlight and use it for propulsion. Light sails are not science fiction. We have built them, small ones, experimental ones. Japan's IKA Arrow's mission deployed a light sail in 2010. It worked. Sunlight pushed it, accelerated it, changed its trajectory. The Planetary Society launched LightSail 2 in 2019. Again, success. The concept is proven. It is real. Now imagine a civilization far more advanced than ours, millions of years older. They want to explore the galaxy. But rocket fuel is limited. Chemical propulsion is inefficient, so they build light sails. Thin, reflective, kilometers across. They launch them into interstellar space. The sails catch the light of their home star, accelerating slowly, continuously. Over years, they reach tremendous speeds, a fraction of the speed of light, enough to cross interstellar distances in reasonable timescales. For them, these sails travel for millions of years, visiting star after star. Some are robotic probes, some carry instruments. Some are simply beacons, markers, meant to be found. And one day, one of these sails passes through our solar system, tumbling, no longer under active control, perhaps damaged, perhaps derelict, perhaps simply on autopilot. It reflects sunlight, and that light pushes it, accelerates it. Exactly as we observed. It is thin, so thin that it appears elongated when viewed edge-on, like a sheet of paper seen from the side. It is dark, weathered by millions of years of cosmic rays, its reflective coating degraded, but still functional enough to catch light. It tumbles, end over end, because the sail is no longer stabilized, no longer guided, just drifting. Could this be Oumuamua? Loeb argued it was possible. Not proven, not certain, but possible. And worth considering. The scientific community reacted strongly. Many rejected the hypothesis. They argued that natural explanations, however imperfect, were still more likely than artificial ones. Occam's razor. The simplest explanation is usually correct, and an alien light sail is not simple. It requires the existence of extraterrestrial intelligence. It requires that they built interstellar probes. It requires that one of those probes happened to pass through our solar system. It requires an extraordinary coincidence. Too many assumptions. Too many leaps. Better to assume Oumuamua is a comet, even if it is a weird comet. Even if we cannot see the outgassing, even if the shape is unusual, nature is strange. Nature surprises us, but nature is still more likely than aliens. Others were more measured. They acknowledged the limitations of the comet hypothesis. But they also pointed out the limitations of the light sail hypothesis. If Oumuamua were a light sail, why did it not decelerate when it approached the sun? A functioning sail could adjust its orientation, catch more light, slow down, perhaps even enter orbit. But Oumuamua did not. It simply passed through, accelerating outward, as if unpowered, as if inert. And if it were a derelict sail, why did it tumble so smoothly? Why not chaotic rotation? Why not torn or fragmented? A millions of years old piece of debris should show signs of damage. But Oumuamua's light curve was almost mathematical, elegant, consistent, as if the object were intact. The debate continues. Papers have been published, arguments made, data reanalyzed, but no consensus has emerged. Oumuamua remains ambiguous, frustratingly so. Some see a comet. Some see a fragment. Some see a fluke of nature. And some see the possibility, however remote, of something else. Something we have never encountered. A piece of technology from another world. Not a message, not a greeting, but an artifact, a relic, a tool long since abandoned. Drifting through the galaxy, serving no purpose, carrying no intent, just existing, waiting to be found. We may never know the truth. Oumuamua is gone. We cannot study it further. We cannot send a probe to catch it. We cannot examine its surface. All we have are the observations, the measurements, the light curves, the spectra, and the arguments, natural or artificial, rock or sail, accident or evidence. The question remains, and perhaps that is fitting, because Oumuamua was always a mystery, from the moment it appeared to the moment it vanished. A shape we could not quite resolve, a motion we could not quite explain, a visitor we could not quite understand. And maybe that is the real message, not that we have been visited, but that the universe is full of things we do not yet comprehend, objects that defy our models, phenomena that challenge our assumptions, mysteries that linger, waiting for better tools, better theories, better questions. Oumuamua reminded us of our limitations and our possibilities. It showed us that the cosmos is stranger than we imagine, and that we still have so much to learn. Whether it was a comet or a sail, a rock or a relic, it was a gift, a moment of wonder, a glimpse of the vast, unknowable deep, and for that, we should be grateful. Let us explore the light sail hypothesis more deeply, not to advocate for it, but to understand it. Because even if Oumuamua turns out to be a comet, the idea of light sails is scientifically fascinating and worth our time. Light carries momentum. This is a fundamental fact of physics. Photons, the particles of light, are massless, but they have energy. And when they strike a surface, they transfer momentum. They push. The force is incredibly small, imperceptible on Earth. But in space, where there is no friction, even tiny forces accumulate. Over time, they can accelerate objects. This is the principle behind solar sails. A large reflective surface catches sunlight. The photons bounce off, and in bouncing, they push the sail. The more surface area, the more photons caught. The more push. The acceleration is slow, gentle, continuous, but it never stops. As long as there is light, there is thrust. No fuel required, no exhaust, no moving parts, just a reflective sheet and a star. For interstellar travel, this is ideal. Rocket fuel is heavy. The more fuel you carry, the more mass you have to accelerate. It becomes a diminishing return. You burn fuel to carry fuel. Chemical rockets can reach speeds of tens of thousands of miles per hour. But that is not nearly fast enough for interstellar travel. The nearest star is 4 light-years away. At 10,000 miles per hour, it would take 70,000 years to get there. Too slow. But a light sail does not carry fuel. It accelerates continuously for years, decades, as long as it is near a star. In principle, a light sail could reach 10 to 20% the speed of light, perhaps more. At that speed, the nearest star is only 20 to 40 years away. Still a long journey, but within the realm of possibility for a sufficiently advanced civilization. So, how would you build one? The material would need to be strong, and light, and reflective. On Earth, we have experimented with materials like mylar, aluminum-coated plastic, thin, flexible, reflective, but fragile, easily torn, not suitable for million-year journeys through interstellar space. A true interstellar light sail would need something better, perhaps graphene, a single layer of carbon atoms, arranged in a hexagonal lattice, stronger than steel, but incredibly thin, 1 atom thick, or perhaps something we have not yet discovered, a metamaterial, engineered at the molecular level, designed specifically for this purpose. The sail would need to be large, kilometers across, to catch enough light for meaningful acceleration, but also thin, less than a millimeter, perhaps far thinner, to minimize mass. The thinner it is, the greater the acceleration for a given surface area. Imagine a sheet the size of a city, but as thin as a sheet of paper, or thinner, drifting through space, catching starlight, accelerating slowly, year after year. Over time, it reaches tremendous speeds, and it travels for millions of years, passing star after star, until one day it enters a solar system, ours. Now, what would such an object look like if we saw it? From a distance, it would be hard to detect. It reflects light, but only if the light hits the right angle. And in space, most angles are wrong. The sail would appear very dark most of the time, only occasionally catching the sun's rays just right, flashing briefly, then disappearing again. Its shape would be strange. If seen edge-on, it would appear as a thin line, highly elongated, a needle, but if seen face-on, it would appear round or square, or whatever shape it was designed to be. The tumbling would change the apparent shape constantly, brightening, dimming, elongating, just as Oumuamua did. The acceleration would be directed away from the sun, because that is the direction the light pushes, exactly as Oumuamua accelerated. And there would be no visible exhaust, no outgassing, no tail, just motion, silent, unexplained by ordinary means. Again, exactly as Oumuamua. The match is intriguing, but it is not proof, because the same observations can be explained, however imperfectly, by a comet with minimal outgassing. The question becomes one of likelihood. Which is more probable? A comet shaped like a needle that outgasses invisibly? Or a light sail from another civilization? Most scientists choose the comet. Because we know comets exist, we have seen thousands of them, we understand their behavior. Even if Oumuamua is unusual, it is still more likely to be a comet than an alien probe. Because alien probes are hypothetical. We have never seen one. We have no evidence that they exist. To conclude that Oumuamua is artificial, we would need extraordinary evidence. And we do not have it. We have ambiguous data. We have puzzling observations. But we do not have a clear signature of technology. No radio signals, no infrared emissions, no patterns in the light that suggest structure or design. Just a tumbling object, dark, silent, strange, but not definitively artificial. Still, the hypothesis serves a purpose. It reminds us to think broadly, to consider possibilities we might otherwise dismiss. Science progresses by questioning assumptions, by exploring unlikely ideas. Sometimes the unlikely turns out to be true. Continental drift was once considered absurd. Black holes were thought to be mathematical curiosities, not real objects. Quantum mechanics defied common sense. But all of these ideas, once controversial, are now accepted because the evidence demanded it. If one day we find clear evidence of extraterrestrial technology, it will likely come from an unexpected place, a strange signal, an anomalous object, something that does not fit our models. Oumuamua was such an object. And while the evidence does not support the artificial hypothesis, the fact that we are asking the question is significant. It shows that we are open to the possibility, that we are looking, that we are ready, at least in principle, to recognize intelligence if we encounter it. Even if Oumuamua turns out to be a rock, even if every future interstellar object is natural, the question will remain: are we alone? Has anyone else explored the galaxy? Have they left traces, artifacts, messages? And if so, will we recognize them? The light sail hypothesis is a thought experiment, a way of asking, what would evidence look like? And that is valuable, because if we never ask the question, we will never be prepared for the answer. Oumuamua may not be a light sail. It probably is not. But it has taught us to imagine, to wonder, to consider the universe not just as a collection of rocks and gas, but as a place where intelligence might exist, where civilizations might rise and fall, where technology might drift, forgotten through the dark, and where, one day, we might encounter something truly extraordinary, not on Oumuamua, but perhaps on the next visitor, or the one after that, or the one after that, because Oumuamua was the first, but it will not be the last. The galaxy is vast and full of wanderers. Some are rocks. Some are ice, and perhaps, just perhaps, some are something else, waiting to be found. When the speculation quiets, we return to the data, because data is what we have, not guesses, not preferences, just measurements, light curves, spectra, positions, numbers. Let us walk through what we actually learned about Oumuamua. what the instruments revealed, what the scientists measured, and what those measurements can and cannot tell us. First, the trajectory. Oumuamua entered the solar system from above the plane of the planets. It came in at a steep angle, roughly perpendicular to the orbits of Earth and the other worlds. This is unusual for objects from within the solar system. Most asteroids and comets stay relatively close to the ecliptic plane, the flat disk where the planets orbit. But Oumuamua came from above, plunging downward. Its path carried it inside Mercury's orbit, close to the Sun. About 23 million miles at its nearest approach. For reference, Mercury orbits at an average distance of 36 million miles. So, Oumuamua came closer to the Sun than the innermost planet. It would have been hot, very hot. The surface temperature likely exceeded 500 degrees Fahrenheit. Hot enough to vaporize water ice. Hot enough to sublimate frozen carbon dioxide. Hot enough to drive off any volatile materials. And yet, we saw no signs of outgassing. After passing the Sun, Oumuamua swung outward. Its speed carried it past Earth's orbit, past Mars, past the asteroid belt, heading toward the outer solar system, and beyond. We detected it only after it had already passed perihelion, already on its way out. By the time we noticed it, the closest approach had happened weeks earlier. We missed the moment when it was brightest, nearest, most observable. Second, the brightness. Oumuamua's apparent magnitude varied wildly, from about 19 to about 21. For context, the human eye can see stars down to magnitude 6 under dark skies. The Hubble Space Telescope can see objects as faint as magnitude 31. Oumuamua was detectable, but only just. And its brightness changed. Over a period of 7.3 hours, it would brighten by a factor of 10, then dim again, then brighten. A smooth, periodic variation. This told astronomers that the object was rotating, and that the shape was highly elongated. Computer models suggested a length-to-width ratio of at least 5 to 1, possibly 10 to 1. Some estimates went even higher. But without direct imaging, it was impossible to be certain. All we had were the brightness curves. And those curves were consistent with a long, tumbling object. Third, the color. Spectroscopy allows astronomers to measure the color of an object with great precision. Different materials reflect different wavelengths of light. Red, blue, infrared, ultraviolet. By analyzing the reflected light, we can infer the composition. Oumuamua's spectrum was red. Specifically, it matched a class of objects known as D-type asteroids, one in the inner solar system, but common in the outer regions. The red color comes from organic compounds. Tholins. Complex molecules formed when simple hydrocarbons are exposed to ultraviolet light and cosmic rays over long periods. Millions of years, perhaps billions. The presence of tholins suggested Oumuamua had been exposed to the harsh environment of space for a very long time. Longer than most objects in our solar system, because it had been traveling through interstellar space. No protective magnetosphere, No nearby star to warm it. Just the cold, radiation-filled void between stars. Fourth, the lack of emissions. Astronomers trained radio telescopes on Oumuamua, listening for signals. Any sign of artificial transmissions, none were detected. Infrared telescopes searched for heat. Any sign of internal activity, none were found. Spectroscopy searched for gases, water vapor, carbon monoxide, carbon dioxide, anything that would indicate outgassing, nothing. Oumuamua was silent, inert. It reflected sunlight, but it emitted nothing. This was one of the most puzzling aspects, because comets outgas, especially when close to the sun, and Oumuamua had been very close. Hot enough to vaporize ice, but no coma formed, no tail appeared. Some scientists argued that the outgassing must have been very faint, below the detection threshold of our instruments, enough to cause the observed acceleration, but not enough to see. It was possible. But it required the outgassing to be perfectly calibrated, just enough to push, not enough to see, a delicate balance. Fifth, the acceleration. This was measured with exquisite precision. By tracking Oumuamua's position over many nights, astronomers could calculate its velocity. And they noticed a deviation. The object was accelerating away from the sun at a rate of about 0.00001 feet per second squared, an absurdly small number, but measurable, definite. The acceleration was not constant. It decreased as Oumuamua moved farther from the sun, exactly as you would expect if the force were related to sunlight, either radiation pressure or comet-like outgassing driven by solar heating. The closer to the sun, the stronger the effect; the farther away, the weaker. This pattern was consistent with both hypotheses: a light sail being pushed by photons, or a comet releasing gas that acts like a rocket engine. The data could not distinguish between them. Sixth, the search for fragments. If Oumuamua were fragile, it might have broken apart, especially during its close pass by the sun. The heat, the tidal forces, the stresses. Astronomers searched for debris, any sign of smaller pieces trailing behind. None were found. Oumuamua appeared to be intact, a single object, not a rubble pile, not a loose collection of fragments, but a coherent body, strong enough to survive the encounter with the sun. Seventh, the rotation. The 7.3-hour tumbling period was stable. It did not change over the course of the observations. This suggested that Oumuamua was not shedding mass. If it were outgassing significantly, the jets would act like tiny thrusters. They would change the rotation, speed it up, slow it down, make it wobble. But Oumuamua's rotation remained steady, mathematical, predictable. Another piece of evidence against vigorous outgassing, but not definitive, because faint symmetrical outgassing might not change the rotation. If the gas escaped evenly from all sides, the forces would cancel, no net torque, no change in spin. It was possible, but again, it required specific conditions. Eighth, the trajectory after departure. Astronomers continued to track Oumuamua as long as they could, watching it fade, grow dimmer, slip away. Its path took it toward the constellation Pegasus. It will travel for hundreds of thousands of years. Eventually, it may pass near another star, or it may wander forever, alone, in the dark. We will never see it again. It is too far now, too faint. Beyond the reach of even our most powerful telescopes, all we have left are the measurements, the data collected during those few weeks in late 2017, and the questions. So many questions. What was it? Where did it come from? Why did it accelerate? The data revealed much, but it did not reveal everything. And perhaps that is the nature of discovery. We see enough to know something is unusual, but not enough to fully understand. We glimpse the mystery, but not the solution. Oumuamua left us with more questions than answers. But those questions are valuable. They push us to build better instruments, to search more carefully, to think more creatively. Because the next interstellar object is out there, somewhere, traveling through the dark. And when it arrives, we will be ready. We will have better telescopes, better detectors, better models. We will see it sooner, track it longer, learn more, and perhaps one day we will answer the questions Oumuamua raised, not with speculation, but with data. Clear, definitive, undeniable. Until then, the mystery lingers, a gift from the stars, a puzzle written in light, waiting for us to solve it. Oumuamua was the first interstellar object we detected, but it was not the first to visit. It cannot have been. The universe is too old. The galaxy is too vast. Objects have been wandering between stars for billions of years, long before we were here to see them. So how many have passed through our solar system, and how many did we miss? The answer is both humbling and exciting. Astronomers have run simulations. Based on the detection of Oumuamua, they can estimate how common such objects are. If we found one in just a few years of searching, there must be many more, most too faint to see, most passing through regions we are not watching, most moving too fast or at the wrong angle to be detected. The calculations suggest that at any given moment, there could be dozens of interstellar objects within the orbit of Neptune. Perhaps hundreds. Most are small, the size of a car, or a house, dark, cold, invisible to current technology. Over the course of a year, thousands may pass through the inner solar system, unnoticed, unrecorded, ghosts in the dark. We simply do not have the instruments to see them. Our telescopes are powerful, but space is vast, and most of space is not being watched. We survey tiny fractions of the sky. We look for specific things. Asteroids on Earth crossing orbits, supernovae in distant galaxies, exoplanets around nearby stars. But a small dark object moving quickly through the outer solar system, easy to miss, very easy. Oumuamua was discovered only because it passed relatively close to Earth and because pan-stars happened to be looking at the right patch of sky at the right time. Luck, timing, chance. Had it passed 6 months earlier, we might not have seen it. Had it been half the size, we would not have seen it. Had it been 10 times farther away, invisible, so we missed countless others. But now we are looking. Now we know what to search for: hyperbolic orbits, fast-moving objects, trajectories that do not match solar system origins. And we are finding more. In 2019, just 2 years after Oumuamua, another interstellar visitor was detected. This one was different, easier to classify, less mysterious. Its name was Borisov 2I Borisov. The second interstellar object, discovered by amateur astronomer Gennady Borisov using a homemade telescope in Crimea. Borisov was a comet, no doubt about it. It had a coma, a bright, fuzzy cloud of gas and dust surrounding the nucleus, a tail stretching behind it as it moved, clear signs of outgassing, water vapor, carbon monoxide, cyanide, all detected spectroscopically. This was what a comet should look like: active, volatile, rich, behaving predictably. Borisov's shape was not extreme. No wild elongation. It appeared round, or at least irregularly round, like a typical comet. Its color was similar to some comets in our solar system: reddish, organic, rich, but not unusual. Its acceleration was easily explained. Outgassing, pure and simple. The jets of gas pushed it, changed its trajectory, exactly as expected. Borisov was, in many ways, unremarkable. A comet like millions of others. The only difference was its origin. It came from another star, another planetary system, and that made it extraordinary. Because Borisov showed us that other star systems have comets just like ours, made of the same materials: water, ice, dust, organic molecules, the building blocks of life, universal, common, expected. Borisov was reassuring. It fit our models. It behaved as predicted. It did not challenge our understanding. Unlike Oumuamua, the contrast between the two objects is striking. Oumuamua, dark, silent, elongated. Mysterious. Borisov, bright, active, round, familiar, both interstellar, both visitors from the deep, but completely different. This tells us something important. Interstellar objects are diverse, just like objects in our own solar system. Some are comets, some are asteroids, some are icy. Some are rocky, some are active, some are inert. There is no single type of interstellar object. There is variety, complexity, richness, and now that we are looking, we are finding them. In the coming years, new telescopes will come online. The Vera Rubin Observatory, previously called the Large Synoptic Survey Telescope, located in Chile. It will survey the entire visible sky every few nights, automatically, continuously, looking for anything that moves, anything that changes. The Vera Rubin Observatory is expected to detect dozens of interstellar objects every year, perhaps hundreds. We will build a catalog, a database of visitors. We will measure their shapes, their colors, their compositions. We will track their orbits, trace them back, try to identify where they came from. We will compare them, look for patterns, understand the diversity. Some will be like Borisov, Ordinary comets, familiar, expected. Some may be like Oumuamua, strange, ambiguous, challenging. And perhaps one day we will find something even stranger. Something that cannot be explained by natural processes. Something that demands a different interpretation, not because we want to find it, but because the data forces us to. Until then, we watch, we wait, we search. Because the visitors are coming, they always have been. We simply did not know how to see them. Now we do, and the universe is revealing its secrets, one wanderer at a time. Oumuamua was first, a mystery, a puzzle, a gift. Borisov was second, a confirmation, a reassurance, a familiar face in a strange place. And there will be a third, and a fourth, and 100th, each one teaching us something new about the galaxy, about planetary systems, about the debris that drifts between the stars, about the universe we inhabit. We missed so many, but we will not miss the next ones. We are ready now, watching, listening, waiting for the scouts, the messengers, the travelers from deep time. They are out there, moving through the dark, and soon they will arrive. In the end, Oumuamua is more than an object. It is a teacher, a reminder, a challenge. It teaches us humility. For all our telescopes and instruments, we nearly missed it. For all our knowledge of physics and astronomy, we cannot fully explain it. For all our confidence in our models, nature surprised us. Oumuamua reminds us that the universe does not owe us clarity. It does not owe us easy answers. It simply is complex, vast, indifferent to our need for understanding. And yet, we search, we measure, we theorize, because that is what we do. That is what makes us human. The desire to know, to understand, to make sense of the cosmos. Oumuamua also teaches us patience. We had only a few weeks to observe it, a narrow window, a fleeting opportunity, and we made the most of it. But it was not enough. We needed more time, more data, more opportunities. Next time, we will be ready. We will detect the visitor sooner, track it longer, perhaps even send a spacecraft, an interstellar intercept mission. Fast, agile, equipped with cameras and spectrometers, capable of flying alongside the object, photographing it, analyzing it, answering the questions that Oumuamua left behind. Such missions are being designed now. Concepts, proposals, studies, they are not easy. Interstellar objects move fast. Catching one requires tremendous speed, precise timing, years of travel. But it is possible, and Oumuamua has motivated us to try. Oumuamua also teaches us perspective. We live on a small planet, orbiting an ordinary star, in a quiet corner of the galaxy, and yet the galaxy comes to us. Objects from distant stars pass through our neighborhood, travelers from systems we will never see, worlds we will never visit, carrying with them the fingerprints of distant suns, the chemistry of alien planets, the history of other stellar nurseries. We do not need to leave the solar system to study the wider galaxy. The galaxy comes to us, one wanderer at a time, and each one is a gift, a sample. a piece of the puzzle. Oumuamua teaches us that we are part of something larger, not isolated, not alone, but connected through gravity, through chemistry, through the slow, patient exchange of matter across the light years. The universe is not static, it is dynamic, flowing. Stars eject debris. Comets escape their home systems. Asteroids drift. And over billions of years, the galaxy mixes. Material from one system reaches another. Atoms forged in distant supernovae end up in our oceans. Molecules formed under alien stars land on our moon. We are all made of stardust. But more than that, we are made of galaxy dust, the shared substance of countless worlds. Oumuamua is part of that story. A chapter in the great cosmic narrative of mixing and migration. It came from somewhere. It will go somewhere else. And everywhere it travels, it carries a piece of its origin, a memory, frozen in rock or ice, waiting to be read. Oumuamua also teaches us to ask better questions. Not just what is it, but why does it exist? Not just where did it come from, but how many others are there? Not just is it natural, but what would artificial look like? These are harder questions. They require us to think beyond the familiar, to imagine possibilities we have not encountered, to prepare for discoveries we cannot predict. Oumuamua was a test, a challenge to our methods, our assumptions, our readiness. And we learned that we need better detection systems. We learned that we need faster response times. We learned that we need more open minds. And we learned that the universe is full of surprises, some small, some profound, but all worth our attention. Finally, Oumuamua teaches us wonder. That deep, quiet sense of awe that comes from encountering the unknown. A shape we cannot quite explain, a motion we cannot quite predict, a visitor we cannot quite understand. It reminds us that exploration is not finished. That discovery is ongoing, that the universe still has secrets, and that we are privileged to live in a time when we can search for them. Oumuamua is gone, speeding away, fading into the black. But its legacy remains in the questions it raised, in the conversations it sparked, in the missions it inspired, and in the quiet reminder that we are not alone in our curiosity. The universe is vast, and it is watching us, just as we are watching it. Oumuamua was the first interstellar object we detected, but it will not be the last. More are coming. And we will be ready, with better eyes, better questions, and better wonder, because that is what Oumuamua taught us: to look, to question, to marvel, and to never stop searching for the visitors, the wanderers, the messengers from the stars. And so we come to the end of our story. The story of Oumuamua, the alien object that visited Earth, or more precisely, that visited the Sun, that passed through our solar system, that caught our attention for a few brief weeks, and then vanished. We have explored its discovery, its shape, its mysterious acceleration, its ancient journey, the debates it inspired, the hypotheses it generated, the data it left behind, and the lessons it taught us. Oumuamua remains a mystery, perhaps It always will. We may never know for certain what it was. A comet, an asteroid, a fragment, a fluke, or something else entirely. But the uncertainty is part of the beauty. It reminds us that the universe is not a solved problem. It is an ongoing exploration, a conversation between us and the cosmos. We ask questions. Nature provides clues, sometimes clear, sometimes ambiguous. And we continue the dialogue. As you drift off to sleep tonight, consider this. Oumuamua is still out there, moving away from us at 60,000 miles per hour. Silent, cold, alone. In another 100,000 years, it may pass near another star. And if that star has planets, and if those planets have observers, they may see it too. A faint streak of light, a dark, tumbling shape, a visitor from the deep. And they will wonder, just as we have wondered. What is it? Where did it come from? And are we alone? Perhaps they will give it a new name, in their language, and perhaps they will tell stories about it, just as we have. The universe is full of such wanderers, objects that travel, that cross paths, that carry with them the memory of distant places. And we are lucky, so very lucky, to live in a time when we can detect them, study them, marvel at them. Oumuamua was a gift, a brief, fleeting glimpse of the interstellar wilderness, a reminder that the galaxy is alive with motion, with history, with mystery, and with possibility. Thank you for joining us on this journey, for exploring the science, for embracing the wonder, and for allowing your mind to drift through the vastness of space. If you enjoyed this sleepy science night, please consider subscribing. We create long-form documentaries designed to soothe, educate, and inspire. Sleep well, dream deeply, and remember, the universe is vast, but it is not empty. It is filled with wanderers, travelers, messengers. And one day, we may be the wanderers, traveling between the stars, passing through distant solar systems, leaving behind our own mysteries for others to discover. Until then, we watch, we wait, we wonder. Good night.